Welcome back, everyone. Next to me is Johan, all the way from Barcelona, I think it was. You are from Barcelona, right? Yeah,
Barcelona,
you're
yes.
from Barcelona. Last lecture of the day here in the auditorium. Yeah, well, Johan, it's up to you, and afterwards I will come back to you.
Thank you.
Maybe with some questions from the audience. Good luck.
Thank you very much. Okay, thanks to you for coming today and share this time with me. I will be quite fast because we have a lot of material to cover. I will try not to repeat too many things because I attended some seminars or some presentations and I got some material that is quite close, but I will try to go to some details on the technologies that we are implementing for high performance and especially high channel count kind of systems in both generation and acquisitions. And you will see I will try to show how these things are done and how things are solved and how we can get the performance we get. And I will go also over the performance that we can get with these technologies. So basically, what we are going to do today is showing why and how the multi-channel systems for RF signal generation and acquisition are necessary, in which areas are important to be used. Also, we will talk about how to address these requirements with the current state of the art, with the current technology. So we will see more traditional solutions and especially the new full digital solutions that we are proposing as a company, as a Tabor Electronics company that we will be introducing the solution today. And finally, we will go into some examples where you can see how these technologies can be applied to different application areas, and especially what is going to be the performance you can expect from those systems. If you have a very clever system, but the performance is not there, it doesn't matter because you cannot perform the test that you want to perform. So when you have systems requiring multiple RF channels, both of generation and acquisition, typically one of the common things that you may have found is that it's not only multiple channels. They have to work together, and somehow they have to work together because they are not working independently. In some applications they are. You may be interested in generating real traffic of Wi-Fi in automotive testing, for instance. You may be interested in generating Wi-Fi signals, DAV signals that don't work together. But for phase array radars, for quantum computing, you need to work with multiple channels working at the same time, working synchronously, and many applications working coherently. So phase, channel-to-channel phase, has to be controlled as well. Another important thing is scalability. Multiple channels a few years ago meant things like maybe 2, 4, 5 channels, 10 channels. Today we may talk about hundreds of channels. In massive MIMO, in quantum computing, actual quantum computing, in many applications you may find actually tens, even hundreds of channels that cannot be really handled in a traditional way. Well, another trend is that wireless signals are becoming more and more complex, and tests are also becoming more and more complex, and many times it's not sufficient by generating simple modulations. You have to provide higher levels of the protocol stack, from just random payload to full implementation of some protocols, wireless protocols, or flexible, agile support of applications like electronic war or radar systems. And this gives us another level. In some cases, this cannot be done deterministically. So you cannot set up an experiment previously, as it was the traditional approach. In some cases, you have to interact with the device under test in a non-synchronous or non-predictable way. And the only way to get this is by applying things like real-time signal processing or closing the loop in real time. So those are the trends, common requirements. A very interesting example is MIMO. In MIMO, you have multiple transmitters and multiple receivers working together. and you have to send different signals and receive different signals and then process them before being transmitted or or after being received. And then you have to control the phase and you have to coordinate all the contents so everything makes sense. So this means multiple channels working together in a synchronous, coherent way. This is not only producing multiple signals at different antennas, it is coordinating them to work together as a real system does. Another important interesting factor is that the bandwidth of those signals is increasing in a way that is constant, relentless. So in the past, a Wi-Fi signal was something like 10 megahertz, 40 megahertz modulation bandwidth. Right now, we are talking about technologies going beyond 200 megahertz or even beyond 2 gigahertz bandwidth. So this means that you have to be able to handle this kind of modulations. So that's an area of application where you need this kind of application with massive number of channels. Phase array radar is another one. The same thing. You have multiple receivers and multiple transmitters working together to transmit even more than one beam at the same time. So you have to provide enough generation support and also analysis support to work over multiple beams, over multiple targets. So you can steer the beam of the phase array or the ESA radar. So traditionally, as we will see, the most typical situation was one single pulse generator, an RF signal, and then you would be controlling only the phase of these different antennas. This is good for a beam forming, but you cannot work with more than one beam. Or if the bandwidth of the modulation signal is too wide, you're not going to get the right signal at the output. We will see something like this later. Quantum computing. Quantum computing is a very typical situation where you have, where you have multiple channel AWG, multiple LOs generators, and then different mixers and modulators. So because each qubit requires multiple output channels, multiple RF signals, this means that when you scale up quantum computing systems with tens of or even hundreds of qubits, this is multiplying by 100 factor or 200 factor. So we're talking about hundreds of channels in a single system. And in order to be able to work in such an environment, you have to support always multiple types of signals, both RF and baseband, and you have to support very low latencies in the order of hundreds of nanoseconds and microseconds because you have to close the loop. You have to be able to generate your signal, get your readout, and then depending on the result, go into the next step in the quantum computing algorithm. Another example is in car infotainment systems. As I said before, you may be willing to generate multiple wireless and broadcast signals at the same time, both reception and transmission, and you need to generate flexibly many kinds of signals working as in real life to test those systems. And you may find from broadcast technologies, DVB-T, or up to navigation signals, whatever, at the same time. Okay, with the traditional RF architecture, what you have been done for many years is basically use devices like this, rack and stack kind of instrumentation, where you can have very high quality, high performance signal generators and signal analyzers to work with those kind of signals. Those instruments are very powerful, they are very accurate, but they have different problems. One is the number of independent signals they can generate. They are limited to one or a few of those signals. They are difficult to configure. There is no way to get a system that can close the loop in a real-time fashion because you need to have a computer controlling everything in the middle. So those are difficult to escalate, and the cost per channel is too high for implementation requiring tens of channels. This cannot be done in this way. There are some new RF test architectures where you have the same kind of functionality, but with a much lower footprint. And because you get rid of so many components that add to the price and to the size, then you can pack together much more channels in a single system, in a single device. For instance, here we have 40 AWG channels, RF AWG channels in a single 19-inch rack, working up to 13 gigahertz. So this means that what you needed tens of the other instruments, here you can do it in a single chassis in a 19 inches rack space. Okay, so what is the trick to get this performance? Basically, to implement everything, both the acquisition and the generation, in a fully digital fashion. So we get rid of mixers, all the microwave plumbing, all the connections, all the, the expensive and very difficult to integrate microwave modules that are typical in super heterodyne kind of architectures. So that's the important thing. Okay, because we have this, we have higher modulation accuracy. As in the previous presentation was shown, digital means numerical. Numerical means that you don't have any error because of the analog nature of the multipliers or the others that you're using in the system. You use, of course, also local oscillators that are digital as well, numerical control oscillators. So you can, because it's digital, you can do also an interesting thing, which is instead of generating just one modulated signal in one channel, now you can generate any number of them at the same time, which is very important in some applications. For instance, in radar, you can generate the signals for 2 different targets. In quantum computing, you can generate the readout pulses for different frequencies over the same cable. These kind of things can be done very gracefully when you do that digitally. Very high channel density, very low cost per channel compared to the traditional technologies. Very scalable because we're talking here is of modular architectures. This is PXI. It's an industry standard for integration of systems, so you can add modules from many different vendors, and this is as simple as plugging the module into the backplane, and that's it. Okay, so because of the architecture, we can integrate in the same bots the generator and the acquisition system. And because of that, it's very easy to implement inside the same bots all the DSP platform or the DSP engine that can allow us to do data reduction, to create signals in real time, or to close the loop in a quantum computing system without having to go to the control computer. Okay, so this is the traditional situation. You have a 2-channel AWG, a continuum wave generator that provides for the local oscillator signal, and then you modulate an external IQ modulator using the INQ baseband data. As you know, the wider the bandwidth is, the more difficult it is to have a very good alignment here. So it's very difficult to have problems with things like quadrature imbalance or quadrature error, carrier feed through these kind of situations because of that. And this is even worse when going up in modulation bandwidth. What we are proposing here is this another architecture. One single channel can produce your signal in either the first or the second or the third Nyquist zone. So depending on the application, you can live with the signal here, or you can work with signals in the upper application and the other Nyquist zones. As far as you have the good enough spurious-free dynamic range, it's okay. The only thing that you need, if you want to get rid of the other images, is a good bandpass filter, which is something quite easy to implement and to add to the system. Okay, the real trick to get this level of performance and this convenience is to implement internally to this architecture the modulation. And the modulation is done by using what is called a digital up converter. A digital up converter is nothing else but an IQ modulator. And you have an NCO. An NCO is basically a DDS. It's a DDS. As you know, a DDS is a synthesizer that does not include any PLL loop in the system. So basically, you generate here the sine and cosine signal that you are using to modulate, to quadrature modulate the system. What is nice in this architecture is that you can change the frequency just by changing the contents of this register. So you can change frequency from one sample to the next. It's instantaneous, phase continuous. It's free. It's part of the architecture. And this is very important in many applications as well, to be able to change the frequency in a continuous wave, in a typical system, super heterodyne. When you change the frequency, many times you have to stop the generation because there is some spurious signals where you are changing from one frequency to the next. This is not happening here. It's smooth, completely smooth. Another thing that you have in this block diagram here are those interpolators, because in AWGS you can work at any frequency, but at the end you have to match or to meet with the Nyquist criteria of sampling. So you have to sample twice the speed of the maximum frequency component of your signal. Okay, but this is typically much wider than the modulation bandwidth of the signal itself. So this means that in this architecture, we can use modulating signals at that much lower sampling rate, much lower bandwidth, according to the modulation bandwidth that we require. So by using interpolator in real time, we can adapt to the final sampling rate, so we can have all the final sampling rate in the final processing, in the IQ modulation. So this saves memory, but this also improves performance in many situations. It's difficult to explain sometimes, but basically, when you do that directly, when you do from here to here directly, and you modulate the signal using the waveform itself, the carrier, if you want to have a continuous carrier, have to have a integral multiple of cycles in the memory. So when you loop the signal, the phase is kept. So this means that if you have, let's say, 1 microsecond of window, you can only set the frequency with 1 megahertz resolution, in 1 megahertz steps. In here, you simply forget about this. There is nothing connecting this loop window with this NCO. So this means that you can set up the frequency completely independently of the signal itself. If we go to the previous example, and this is very important concept, and this is something that has been given AWG's bad press for some years when generating RF signals. If you look at a D2A converter and you do repeating the signal with the carrier in it, every time you go through the loop, the signal repeats itself exactly the same way. So the quantization noise is repeating also. So all the quantization noise is repeating as multiples, as harmonics of the 1 megahertz signal. So all the power of the noise power goes to these specific spectral lines. So this goes against the spurious free dynamic range. Because you are doing that, this is not happening anymore. So each time that you repeat the signal is slightly different, because the phase of the carrier is not the same. So you spread out all the quantization noise, and just by magic, you get a much better spurious free dynamic range with the same D2A converter. And you can do that with, for instance, in the instrument we have outside, the Tabor Proteus is a 30 microhertz resolution. Okay, so you have a lot of power on that. Okay, so this is the detailed block diagram of the digital lag converter. Okay, so this is already explained. In a more traditional situations, you have this, you can generate multiple signals with your AWG. By doing that, you generate an IF signal, and then you use mixers, and you use a multi-channel local oscillator where you can control the phase to have different phases. Okay, so at the end you can align the phases. So this is just a radar, and then you're looking from this direction. And when you look for this direction, you can get these perfectly matching phases. And then the problem is that when you do that only with the phase of the carrier, when you impose this, of course, the phases are aligned, but the problem is that the pulse itself is not aligned. So you get a pulse that is losing bandwidth. So that's something that you have to avoid in very wideband signals, because you lose your bandwidth by doing that. So when you do this in this situation, you have multiple channels, then you can control the phase, but you can control the delay between the different signals. So you don't have these problems. You have perfect matching signals for multi-channel configurations. The same is true for quantum computing. Okay, so this is an example. Just go to some numbers so you can understand what you can get. First of all, the bandwidth, the usable bandwidth, goes over 13 gigahertz. And because we have implemented that with 9 gigasamples per second, 16-bit sample resolution, we have a very wide usable bandwidth. So you can get very high frequency. What is the modulation bandwidth you can get? Well, it depends on the working mode. But in this particular instrument, we have, for each one of the channels, there is 2 digital up converters, independent, each one with its own NCO. So this means that you can get multiple signals at the same time, independently. So you have IQ data, in 2 pairs of IQ data going to that. So at the end, you have a lot of flexibility. I will show you some examples of that. In this one, a good example. Here you have the example of a control pulse and a readout pulse. In fact, in this is the time domain signal. This is just a detail. But if, in fact, I am sweeping the readout pulse while keeping the control pulse by using the 2 NCOs. So one NCO is fixed and the other one is sweeping, okay, because I use that over the same cable. This is an example of a very wideband signal. This is a ultra-wideband signal, 1.5 gigahertz bandwidth. It's a wide media signal. And here you can see how good can be the modulation quality for such a signal in the second Nyquist band. Talking about spurious free dynamic range, here you see at low frequency we can have something like 95 dBs dynamic range. And this is one of the things giving us this performance is the NCO architecture, okay? At the same time, we can have, those are other examples. This is a LTE signal with 70 dBs of ACPR, or this is a multi-tone signal with over 80 dBs of spurious free dynamic range. And that's a very powerful SLM RF performance. This is, you can see here the Gaussian pulse, and here is all the full first Nyquist zone. Everything is clean, nothing here, just the pulse, no spurious, no harmonics in it. This is another example of very accurate complex modulation. This is both combining the generator and the acquisition system. In here we have a 11A signal, 160 megahertz bandwidth. And what I am doing here is generating it with the generator and acquiring with the digitizer, and I get minus 51 dBs of EVM. The same thing can be applied to the down conversion in the digitizer. Okay, so the same thing exactly can be applied to there. In fact, we support 2 down converters for the digitizer, so you can also get 2 baseband signals from 2 different signals in the system. So you can down convert things like that. Okay, so you can go up to 10 gigahertz with the down converter. This is the complete block diagram. As you see, you have here the dual down converter. So you go to the acquisition memory, or you can also go to the closed loop system in a quantum computing system. And in fact, if you look at the full block diagram, as you see, it's a fully integrated generation and acquisition system. And you have here the FPGA, which is user customizable, where you can also implement your own DSP. You can also our own DSP block library. So you can very easily create your DSP chain without having to implement your IP using VHDL tools. So just using ASCII commands. Okay, so that allows you for closing the loop or for real-time signal generation or data reduction. Okay, so anything that you may require from us, you can contact us at this address. I am based in Europe, so I am fully available to travel around and to contact you at any moment. And also our representative here, that is BFI.
Well, first of all, a big thank you.
Thanks for being tolerant.
There's room for one question, and I have one over here.
I'm very curious, because it's a multi-channel system, and you want to do phase coherent signal generation.
Yeah.
How is the initial calibration of phase arranged? Because at startup, it's a pipeline structure, and you have like sample calibration, but you also have the LO calibration. And how do you know for sure at the outputs what the calibration is?
That's an important issue because I didn't mention that in the presentation, but we have full coherence of phase for the generator side and also for the analyzer side, for the acquisition side. So that's important. Many applications you have to down convert with the same local oscillator that you use to up convert. So we have to synchronize both. And basically, because it's fully integrated, we have some trigger signals internally to start to the phase at a given point at the same time in all the channels. And then what we can set up is the initial value. So by that, we can change the phase from channel to channel. Okay, but we use a hardware trigger, internal hardware triggers that allows us to do this alignment. Once, of course, this is the internal alignment. Then if you have external things, then you have to do your own calibration. We have software for that. So, of course, you may have different cable runs or whatever, and then you need to have even further. But the good point is that we have full control over the phase channel to channel. And I have some demos as well, where you can see how you can change by using a slider. You can change the phase. And again, the phase can be changed on the fly without having to interrupt generation. So it's very spectacular because you see that the signal is changing, but you don't see any spurious in the spectrum because it's changing continuously. The same for frequency as well, but that's an important point. Without this, we could not do that. And we do that at the same time for both the acquisition system and the generation system. So if you have multiple, or you have some relationship with the NCO frequencies, then they keep the phase relationship forever. So that's important for many applications, like quantum computing, for instance, or for radar. For moving MTI and other radars required to keep this coherence over time. And they only have to keep, they have to be known in advance. They have to be repeatable and deterministic. Yeah. Thank you.
Thank you, Joan. If there are any questions left for Joan, visit him at the ACL BFI booth. We now have a short coffee break, but before we go to that, I have a short announcement for the visitors here, but yeah, thanks again, Joan.
Thanks. Thanks to all.